Get this thing right? If you see a closed system, the energy won't be created or destroyed, but it can be converted from one form to the other, right? So if you see that, what are the different forms of the energy we know? The different forms of energy is huge, right? Few are listed over here, such as we are having what? Such as we are having, just 1 minute, I'm recording. Fine. So what are the different forms of the energy? The different forms of the energy are the kinetic energy, the potential energy, the light energy, the solar energy, the heat energy, the nuclear energy, the sound energy, the chemical energy, the electrical energy. There are many forms of energy, right? Now, in this chapter, we'll be mainly concentrating on these two energies, right? Chemical energy and electrical energy. Agreed, right? Now, what happens in an electrochemical cell? In an electrochemical cells, we are converting a chemical energy to electrical energy, right? First kind of cells. Second kind of cells is that we are trying to convert electrical energy to chemical energy. Right? Clear? Right? So these are the two kinds of cells we know, right? In first kind of cell, what we do? We convert chemical energy to electrical energy. In the second kind of cells, we convert electrical energy to chemical energy, right? That's very important, right? Now go to the
Mhm.
next part, right? We have to see that what happens in the first kind of cells. This is called as a Voltaic cell, right? Or it is also called as a galvanic cell earlier, right? And what happens in the second kind of cells? The electrolytic cell. Electrolytic cell you have studied in the GCSEs, right? You can remember, right? You studied in the GCSE, right? See, if you see the GCSE book, right? It's right over here. Just 1 minute. Mhm. See, this is right. You're having this, right? This fine. You had this, right? You had this introduction to electrolysis, changes in electrodes, right? This is GCSE stuff, right? Fine. So we did this, right? That extraction of aluminum, or electrolysis of aqueous solution, right? This was electrolysis, right? So what we do in the what we do in the in this electrolytic cell, we force a non-spontaneous reaction to happen by passage of electricity. Clear? Suppose this reaction NaCl gives you Na plus Cl2, right? And now, is this reaction spontaneous? That if you keep a table salt on the plate, it
No,
automatically it will be giving out chlorine? No. Very good,
no.
brilliant answer, right? It's not a spontaneous reaction. So can we force this reaction to happen? Yes, we can force this reaction to happen by passage of electric current, right? Clear? Understood? By passage of electric current. So this is a very important part. You to understand that when we talk about electrolytic cell, in electrolytic cell, what happens in electrolytic cell? We convert a non-spontaneous chemical reaction into, sorry, we force a non-spontaneous reaction to happen by passage of electric current, right? Now the next part is that if we see that when we discuss about when we discussed about the first kind of cell, Voltaic cell. In the Voltaic cell, what happens? Suppose there's a spontaneous chemical reaction, right? Suppose zinc plus copper sulfate gives you zinc sulfate plus copper, right? Isn't it? There's a spontaneous chemical reaction happening, right? So can we convert this? Can we convert the chemical energy given out of this spontaneous chemical reaction? Any spontaneous chemical reaction gives out energy. Is it clear? Gives out energy by default. Is it clear to you, Hari? Is it clear? Arnav, is it
Yeah,
clear? Any
yeah.
spontaneous chemical reaction gives out energy. Now, this chemical energy, can it be converted to electrical energy? Yes, we can, right? We can. So we can convert the spontaneous chemical reactions chemical energy to electrical energy. This is the most common form of cells which we use in our homes for our luxury life. See, batteries, right? Have you seen the pencil battery? Right, pencil battery is a Voltaic cell. The laptop battery is a Voltaic cell. The cell battery is a Voltaic cell. The car battery is a Voltaic cell, right? Is it clear? Did you get this thing? So now coming to this part, if you see that when we see these kinds of cells, both the cells will be having what? Both the cells will be having both the cells will be having electrodes, right? So what's the definition of an electrode? Electrode is a conductor of electricity, right? What's the meaning of the word called as electrode? Electrode is a conductor of electricity, right? Which is used to make contact with the non-metallic part of the circuit, right? Non-metallic part of the circuit, right? Such as a solution in the cell, right? Now, coming to the part, what are the two kinds of electrodes we know? The two kinds of electrodes we know is what? One is called as the cathode and one is called the anode, right? So if you see electrodes can be of two types. One is called as a anode and one is called as a cathode, right? So this is a very important part we know, right? Next thing is that if we see the electrode, right? Both the electrodes will be behaving similarly in the redox reaction, right? Isn't it? So if you have got a Voltaic cell, cathode will be suffering reduction, anode will be suffering oxidation. Is it clear? Fine, fine. Now, if you see a electrolytic cell, right? In the electrolytic cell, what happens? Cathode will be undergoing reduction reactions and anode will be suffering oxidation reactions. Makes sense, right? Fine.
Yep.
Is it clear? So this is a very important point we are noting, right? Now we have to know the rhyme, right? The rhyme is what? Red cat, right? Red cat, right? Is it clear? Right? Just
Yeah.
guys, just 1 second, just I'm coming. See, when we talk about the rhyme, what rhyme we know? Red cat, right? Red cat. Reduction happens in cathode only. Remember this thing that I have got a red cat, right? I've got a red cat. Remember this thing, right? Reduction happens in cathode, right? Now we go to the next part, right? Whenever we are seeing the electrode sign will be different, right? So if you see when we take a Voltaic cell, right? When we take a Voltaic cell, right? The cathode will be positive, anode will be negative. Is it clear? Fine. Now if we see a electrolytic cell, right? In the electrolytic cell, what happens? In the electrolytic cell, the cathode is negative, anode is positive. Clear, everybody? Understood this thing? See,
Yeah.
I'm telling you both, right? Please stop me if you don't understand. Just a request to you both. Please stop me then and there. That, hey, I didn't understand. Please tell me, right? Please stop me then and there. Don't worry about anything, right? Just stop me then and there. Clear? Now, we are now going to the Voltaic cell, right? In the Voltaic cell, what happens? In the Voltaic cell, there's a spontaneous chemical reaction happening, I told you, right? Suppose zinc plus copper sulfate, right? Suppose I'm taking this zinc plus, just 1 minute, I'm just doing this. Zinc plus copper sulfate gives you zinc sulfate plus copper, right? Isn't it? Fine. Zinc sulfate plus copper, right? So over here, see, if you see that what's the oxidation number of zinc, Arnav, can you tell me, is it combined or uncombined?
Um, Uncombined, so zero.
Uncombined, zero. Brilliant answer. See, such a brilliant brain, right? Now, Harry, what is this? Sulfate will be -2. This will be how much?
+2.
+2. Brilliant answer. Now, in zinc sulfate is -2. This is +2. Now, Harry, copper is combined or uncombined over here? Tell me.
Uncombined, so
Uncombined, so
zero.
it's zero. Brilliant answer. Now, I told you the graduation level way of doing it. It will be helping you, right? This trick, right? Boxes. Make the boxes. Understood, Harry? Enough, right? Whenever you're having any redox questions, that what is the oxidizing agent, with the reducing agent, how it is doing, right? You make the boxes. 0 to, sorry, my bad. See, I'm sorry, please. Huh? Zinc to zinc, right? Right? Zinc to zinc. We are going from zinc to zinc. So what's happening over here? 0 to +2. What's happening? Loss of electrons. So oxidation. Then you write Ra, reducing agent. Is it clear? Now I'm going to here, right? See, copper 2 plus to copper 0, right? Whenever I'm going to copper 2 plus to copper 0, what's happening over here? Copper is going from +2 to 0, right? +2 to 0, right? What is happening over here? Gain of electrons, that is reduction, and oxidizing agent. Is it clear, everybody, right? Clear?
Mhm.
So that's a very important thing. We are seeing what over here? We are seeing over here that zinc is losing 2 electrons. Can you see this? Zinc is losing 2 electrons. Why? Because more reactive element displaces a less reactive element. That we know, right? Please note down this. More reactive element displaces the less reactive elements from its compound. So we are seeing what? This is zinc, this is iron, this is lead, this is hydrogen, this is copper, right? So see, this is the thing you're seeing, right? Isn't it? Fine. Is it clear to you? So if you see that zinc will be higher up in the reactivity, so the more reactive, right? So more reactive species suffers what? Suffers a greater way to lose electrons. Is it clear? Understood? Is it clear to you, everybody? How is it clear?
Yeah.
So loses electron. Anybody who is higher up in the reactivity loses electron. Everybody ask me questions. I'm telling you, right? This is a very important chapter, a difficult one too. But ask me questions, right? Everybody's clear? So zinc will be losing electrons, right? Loss of electrons will be happening. And it goes from what? Zinc to plus, right? Now, copper is accepting electron meekly because copper is below the reactivity series, right? Lower in the reactivity series. Copper will be accepting the electrons, right? Meekfully, right? So what happens? That in the solution, if you take this reaction in a solution, right? You're taking copper sulfate and added zinc. What happens in the solution itself? Zinc will be transferring the electrons to copper, isn't it? Zinc will be transferring the electron to copper in the solution itself. But can we do something? Can we do something where zinc will be transferring the electron to this copper via external wire? Yes, we can, right? We can make something where we can make something scientific way that where zinc will be transferring the electron to copper via external circuit. And we learnt in physics, that you all learnt in GCSE physics, that flow of electrons in a wire is called as what? Harry, you tell me. Flow of electrons in a wire is called as
Electricity.
electricity, isn't it? So we are flowing the electricity, we are flowing the electrons, right, and generating electricity, right? Is it clear? So what we do in order to make this happen, make this important trick happen, we take what? We take two half cells, right? Isn't it? We take two half cells, right? Arnav, who is teaching this in your school? In your school, Mr. Baker is teaching you, right?
Yeah, Mr. Baker.
Maker Baker is touched where now?
Yeah. He hasn't started this yet. We're just behind this.
Okay,
We just finished second results.
okay, fine. Okay, anyways, is it clear? Did you get this thing? So what happens over here? That we're taking two half cells, right? In the two half cells, what we're doing? In the two half cells, we are taking we are taking zinc dipped in zinc ions, aqueous ions, and we are taking copper zinc with dipped in copper 2 plus ions. Is it clear, everybody? Right? What's happening over here? We are taking zinc dipped in zinc sulfate and copper dipped in copper sulfate. Is it clear, everybody? Understood? Fine.
Yeah.
Now this is the half cell you are taking, right? We are taking two half cells because the question in your board papers that if we take a single cell, if we take a single beaker, then zinc will be transferring the electron in the solution itself, and we won't be able to harness the electrons, right? Isn't it? We won't be able to harness the electrons, right? So that's the way we do, right? Now come to the next part. That let's see how it works, right? Isn't it? Till over it's clear to you, everybody, right? Arnav, is it clear?
Yeah.
Harry, is it clear? Thank you so much.
Yeah.
Now, if you see that, how does it work? It will be working something like this. See, over here, see, this is the important picture, right? We are seeing. See, over here, what happens? We have taken zinc in zinc sulfate and we have taken copper in copper sulfate solution, guys, isn't it? We have taken this. Now, what happens? When you don't connect the wires, nothing happens. Nothing happens, right? When you don't cut the wires, right? Nothing happens, right? Nothing happens. But once you connect the wires, right? When you connect the wires, right? Once you connect the wires, immediately you'll be seeing that the electrons will be start to pushed from zinc to copper because zinc is higher up in the reactivity series, right? Isn't it? It will be pushing electrons to copper, right? And how it does? As I have told to you that cathode is what? What happens in cathode, Arnav? What did I tell you? Red cat
Reduction.
reduction happens in cathode. Brilliant. What happens
Yeah.
in anode? We are having oxidation happening in anode, right? Isn't it? Oxidation happening. So that's a very important part we have known, right? Now, whenever we have dipped zinc in zinc sulfate, what happens? And you connected the wire, zinc will be losing to. Let's do one thing. Let me cut paste this in the paintbrush. I can get more space there. Wait, over here. Has the Voltaic cell HL been done in your school, Harry? Has the
Yeah.
Voltaic cell HL has been done, right? He's
Yeah.
on track. He's on track. He's on track. He's on track. Mr. Wells should have taken this. Mr. Wells, he deserves to take this difficult part, I guess. It's a wrong decision. Mr. Wells should have taken this. Born-Haber cycle. These chapters are quite. It tests the metal of the teacher, right? Of the IBDP teacher. So he should have taken it, Mr. Wells and Mr. Arfan. Yeah, thank you so much. See, now can you see this, guys? Huh? Everybody? It might be small enough, right? See, what happens? When we added zinc to zinc sulfate, what happens? Zinc from the zinc metal, right? Zinc from the zinc metal goes to the solution as zinc 2 plus, right? Leaving behind the 2 electrons over here. Clear? Arnav, understood? This is clear?
Yeah.
Zinc goes to the solution as zinc 2 plus ions, right? Ionic form is soluble form, right? It is a soluble form. So it goes to the solution as zinc 2 plus, isn't it? With time, what happens? With time, you'll be seeing that the zinc 2 plus will be accumulated over here, right? Is it clear? Right? Just 1 minute. I'm
Yep.
trying to make it bigger, right? Just 1 minute. Make it bigger. That will better. And see then more, right? Now it's better, right? See. Now, having said this, what happens with time? The thickness of the zinc will be getting thinner and thinner, or thicker and thicker. Arnav, can you tell me?
Thinner and thinner.
Thinner and thinner. That's a really brilliant answer, right? Isn't it, Harry? Right? It goes to the solution as zinc 2 plus, right? Now, in the cathode, what we have taken? We have taken zinc sulfate, right? Fine. So zinc sulfate will be there as zinc 2 plus plus SFO 2 minus. Agreed, right? So with time, what happens? Zinc 2 plus is getting added over here, isn't it? Zinc 2 plus is getting added. So technically, what happens? Zinc 2 plus ions will be increasing in concentration. Understood, right? And slowly, in the anode, you'll be seeing that a positive ions of zinc is increasing, will be increased. Is it clear? Did you get this thing, Arnav? Harry, understood
Yep.
this thing? Now, when you connect zinc and copper with a wire, now the ego game starts. Zinc is like a tiger, right? Zinc is like a tiger, and copper is like a deer. It will be forcing, and zinc will be immediately losing electrons, right? That's the ultimate journey of a more reactive metal, right? It will be forcing the electrons down copper throat, right? Copper is also metal. It wants to lose electrons, but it has got no other choice but other than to accept the electrons of zinc, and the electrons will be coming over here, sitting over here. Now, what do we take in the aqueous solution? Copper sulfate. So copper sulfate will be staying as Cu2 plus plus SO4 2 minus. Agreed, right? Isn't it? Isn't it? Copper 2 plus plus SO4 2 minus, isn't it? Right? Now, now Arnav, can you tell me that who goes towards the cathode? Copper 2 plus or SO4 2 minus, Arnav?
Um, Copper 2 plus.
Copper 2 plus. What about you, Harry?
Yeah, copper 2
Copper 2
plus.
plus, right? Copper 2 plus is going. And what happens in the cathode, Arnav? I've got a red cat in my house, right? Remember this thing. I've got a
Yeah.
red cat. So reduction happens. So copper 2 plus plus 2 electrons gives you copper. And the copper will be deposited over here. Is it clear? Understood? Will
Yeah.
be deposited over here, right? Slowly and slowly. So slowly and slowly the copper plate will be getting, Harry, thicker or thinner or thinner?
Thicker.
Thicker and thicker. Now, can you understand this? With time, this copper 2 plus is getting used up. Understood? Agreed?
Yeah.
And proportionately, sulfate ions will be more in number. Agreed? Fine? Agreed? Fine? Is it clear to you over here? Arnav, is
Yep.
it clear? Harry, is it clear? So it will be more in number, right? Sulfate ions will be more in number, right? That's very important, right? Now, going to this thing, you have to see that whenever we are seeing that in the cathode, what happens? There's an accumulation of the sulfate ions. Is it clear? And the anode, what happens? Anode, there will be accumulation of the zinc 2 plus ions. Agreed? Agreed? Zinc 2 plus ions, right? This will be stopping the cell from functioning. Is it clear? Why? Because on the anode you have got more positive ions, huge positive ions. On the cathode we have got negative ions. This stops the cell from functioning. This is called as liquid junction potential. It comes in exam. What is liquid junction potential? Understood? What is liquid
Yep.
junction potential? In suppose many times the ye come definition come, liquid junction potential is the unequal cation and anion across the junction is called as liquid junction potential. Understood? After a certain amount of time, you'll be seeing that the bulb stops glowing. Understood? The bulb will be switching off. So
Yeah.
what to do? We have to make sure that the cell works, isn't it? Isn't it? Cell works. So what we do? We take the help of a salt bridge. Agreed? Fine. We take the help of a salt bridge. Understood? Clear? We take the help of a salt bridge. In the salt bridge, what we take? We take a very highly concentrated KCl or Na2SO4. Agreed? Right?
Yep.
What we do, we take agar agar jelly, right? Agar agar gel. To this, we are adding loads and loads of KCl or Na2SO4. Understood? Right? We
Yeah.
make like a atta, that atta dough, right? Just Harry, understood? Have you seen atta dough
Yeah.
prior to making that rotis? That kind of, right? You have taken gel and put in the salt, dry salt, and we then what we put this gel inside a bent tube, glass tube. Understood? Clear? Like this. Understood? And we put cotton wool over here. Clear, everybody? Fine. Now, what's the work of the salt bridge? I told you, Harry. The work of the salt bridge is to lower the liquid junction potential. Somehow it has to neutralize the sulfate ions, and somehow it has to neutralize the zinc ions. Is it clear? Everybody is clear?
Yeah.
Got it? Somehow it has to neutralize the zinc ions, somehow to neutralize the sulfate ions. Everybody is clear? Fine.
Yeah.
Now, how does it do it? Now, in this tank, you have got what ions more? Arnav, what are the ions which are more concentrated over here? Tell me.
The SO4 to minus.
Here, see, zinc was going from the plate to the solution as zinc 2 plus, right? Isn't it? What is happening? What is happening in the anode? So, Arnav, your teacher has not done, but still you are trying to absorb things. That's a wonderful thing, Arnav. Don't worry. Did you get this thing, Arnav? Is it clear?
Yeah, I got
So
it.
zinc is going from the solution, so from the plate, metal plate to the solution, and slowly zinc 2 plus ions is increasing, right? Fine.
Yeah.
So
Yep.
from this salt bridge, who will be getting attracted towards the cathode, so the anode? Sulfate ions. Is it clear, Harry? Is it clear, Harry? Is it clear?
Yeah. Yeah.
Sulfate ions will be attracted, and what happens? The sulfate ions will be neutralizing this zinc 2 plus. Is it clear? Understood? Isn't it? Sulfate ion neutralizes this zinc 2 plus to Z and SO4. Is it clear? Now, there's a question of your boards. I hope that you have seen. In a salt bridge, what happens? The anion, they see, you can make a rhyme. The anion goes to the anode. Clear? Understood?
Yeah.
The anion goes to the anode. Is it clear? Everybody's clear? The anion goes to the anode. Is it clear? Fine. Understood this thing? Now, over here, see. Now, if we see in the cathode, which ions are more? Tell me. Sulfate ions are more. Is it clear? Fine. Sulfate ions are more. Isn't it? Because copper 2 plus was going and getting deposited. Hari, is it clear? Arnav, is it clear?
Yeah.
So which ions will be more in number? Sulfate ions will be more in number. See, this is a very difficult topic. I'm telling you that you try to help me, right? Ask me, stop me, then and right, please, huh? You're there for almost 2 years with me, right? Just stop me, right? Plus stop me, right? Is it clear, everybody? Fine. Sulfate ions will be more. So who will be getting attracted from the salt bridge? Tell me. Na plus or SO4? SO4 2 minus. Who? Harry? Who will be getting attracted? In the solution, you have got sulfate ions more in number. Who will be getting attracted from the salt bridge? Na plus or sulfate ions?
Na plus.
Na plus, and what about you, Arnav? Who will be getting attracted towards the sulfate ions, which is more in number over here? Who will be getting attracted?
Yeah. Na
Na plus, right? And what happens? It will be neutralizing it to form Na2SO4. Is it clear? And see, it will be reducing the liquid junction potential. Clear? And the cell starts to function again. Clear?
Yep.
Understood? Clear? Yeah. Fine. So this is the way how the cell works, right? Exactly, this is the way how the cell works. So fine. Now we're going to the important part, that if we see when we discussed about this Voltaic cell, right? This Voltaic cell will be very, very important for us, how they will be working, right? Now, coming to the part, we are coming to the part of the HL part, right? Fine. Guys, if you want to take a screenshot, please take a screenshot, or you can take a screenshot and paste it on the group, right? Arnav or Harry?
Yeah.
Thank you so much. Wait, just wait. This will be better, right? This circle over here, and with the up arrow over here, right? Now you can take a screenshot. Thank you.
Yeah, got it.
Thank you so much. So now we are going to the part of the HL, right? We are going to the part of the HL. Now, if we see when we discuss about the HL part, right? We have to now go to the important concepts which are there, right? The first important concept is what? The first important concept is that when we talk about, is the Bilkin book gone? Here you go, right? Amazing. I really treat Steve Owen as a god, right? Such crispy vocabulary, such to the point understanding, right? So it always try to immediately go it today, right? Isn't it, Harry? Just don't delay anything. Are any exams is there, Harry?
No.
So there won't be any excuses coming up, isn't it? That I couldn't do because of this, isn't it? Because of that, isn't it? So I hope that you all jump today, right? I need today. You have to complete this by today. Whatever, 2 o'clock, 3 o'clock, I don't mind. You have to complete. Everybody is sleeping this, right? On Fridays, they are sleeping for 4 hours. I can tell you the examples of students across the globe, right? Who are brilliant like you. See, now I'm talking about the electrochemical cell, Voltaic cell, right? The HL part, right? The first important part you have to know is that whenever we are talking about a Voltaic cell, right? How to represent the Voltaic cell? I forgot to tell you how to represent this particular Voltaic cell. We represent this Voltaic cell as this. See, on the anode we have taken zinc, so Zn slash Zn2 plus Aq. Got it? How to represent the half cell? By this. Is it clear? Arnav, is it clear? Harry, is it clear?
Yep.
Then we show the Sol bridge sign. Sol bridge sign will be showed by a double arrow, right? Fine, double. Then we do what? Then we write the ions which is there over here, copper 2 plus, Cu2 plus slash Cu, solid. Clear, everybody? Fine. This is the way we represent this entire Voltaic cell, right? Is it clear? A cathode on the right hand side, anode on the left hand side, and we show the solvage with a double line. Clear? Fine, everybody? Got it?
Yeah.
Now, next important thing is that, you know what? You have to understand what does this single line means. The single line means that it shows, it is telling about a phase difference, right? Isn't it? Isn't it? It's a solid. See, it's a solid. It is in contact with the different phase, AQ, right? So you have to draw a single line over here, right? Now, we do now understand a very important part which is called as the standard cell potential, right? Standard cell potential. What do you mean by standard cell potential? That we have to understand, right? When we talk about standard cell potential, right? What is standard cell potential? Now, standard cell potential is actually nothing but it is the amount of the voltage, right? It is the amount of the voltage produced when two half cells are joined together. Is it clear? Fine. We are taking two half cells. We are taking two half cells. We are connecting them through a voltmeter, right? So the voltage which is coming out when two half cells are joined, right, in standard conditions is called as a standard cell potential. It is represented like this, E cell. Is it clear? What is standard cell potential? Standard cell potential is the voltage when two half cells are connected under standard conditions. Arnav, is it clear? Fine.
Yep.
When two half cells are joined, right? We are joining two half cells. And what is the voltage which is getting over here? That is called a standard cell potential. It is represented as what? E, then cell, CELL, right? And what does this circle means? Under standard conditions, we have put them. What are standard conditions, Arnav? Tell me.
298.5 kelvins and 100 kilopascals.
Wonderful. That was fast also, right? And anything else to add, Harry?
1 atmospheric thing.
1 atmospheric is this only. He has already told about
yeah.
the pressure, right? 1 atmosphere. Anything other than if the solution should be in 1
Moles
mole
or
per
mole,
decimeter
yeah.
Moles per
mole per
decimeter
decimeter.
cube.
So you missed out this. This is the thing, right? 1 mole per decimeter cube. Now, if you see when we talk about the standard cell potential, right? When you talk about the standard cell potential, we can write down this equation, right? It is the electrode potential of the right hand side minus electrode potential of the left hand side. Clear? Is this clear? Fine.
Yeah.
This is, please write down this equation, E right minus E left, right? Now, you to understand that what do you mean by cell potential and what do you mean by electrode potential, right? That's very important. That's not properly discussed in the book, right? Just understand this. What is electrode potential? Electrode potential is the potential of the individual cell, half cell. Clear? Understood? Individual potential of the half cell. This might be having E1 standard electrode potential, and this might have standard electrode potential of E2, right? Is it? Fine. So when we subtract the right hand side minus left hand side, right? Left hand side, this will be giving you the standard cell potential that is described as E dot cell. Clear, everybody? Understood this part? Thank you. Now over here, next is that if we see that when we are trying to discuss about the standard cell potential, right? We to understand that, can we find out the standard electrode potential of these two half cells individually? Somehow we can find out the standard electrode potential of the half cells? No, we cannot. Why? Because we learned there just now that whenever we are taking this bit of Voltaic cell, right? We learned over here that whenever we are taking a Voltaic cell, right? there must be a reduction happening along with oxidation. Is it clear? Is it clear to you? That must be a reduction happening with oxidation. There must be happening this, right? So we cannot find out the standard electrode potential of any half cell in standalone conditions, right? Clear? Because it has to be attached with some cell which will be suffering reduction and giving the and accepting the electrons coming out from over here. How is it clear?
Yeah.
Understood? Arnav, is it clear? Fine.
Yeah.
We cannot find out the standalone electrode potential of any half cell, right? Fine. We
Yeah.
cannot find out, right? But what we do, what we should do, we should find out, right? How we should do? For that reason, to find out the standard electrode potential, right? Electrode potential is what I told you this trick. Individually, the potential of this individual cell is called as electrode potential, right? Electrode potential, right? Electrode potential. Clear? How could you find out the standard electrode potential? To find out the standard electrode potential, what we do, we have to use the standard hydrogen electrode. It's clear, everybody? We have to use the standard hydrogen electrode, right? Now, what does the standard hydrogen electrode look like? Standard hydrogen electrode in many question paper will be seeing the She. What are the conditions of She, right? So don't get worried. So She is what? She is standard hydrogen electrode, right? That is She, right? Now come to the next part. That if we see when we talk about a standard hydrogen electrode, how does it look like? We take a glass test tube, like specialized test tube, and we take a platinum wire. Is it clear? Understood? We take a platinum
Yeah.
wire. Clear? We take a platinum wire. And what we do, we bubble hydrogen gas at 100 kilopascal pressure. Is it clear? What we do, we take hydrogen gas, at 100 kilopascal pressure. See, standard conditions, see, standard. We have to follow the standard conditions also, right? Standard. 100 kilopascal pressure, and we take 298 Kelvin. And the most important thing, now write down in your copy, please. You have to take a monoprotic acid. Write down this thing, right? Fine. Clear?
Yeah.
Is it clear? You have to take a monoprotic acid. Agreed? Right? Fine.
Yeah.
Fine. So this is very important, that if you see that when we talk about the standard hydrogen electrode, we have to take a monoprotic acid. We don't take a diprotic acid, right? Suppose HCl, right? Why? Can you tell me why? Why, Harry? Why we should not take H2SO4? Tell me.
I
Because
forgot this.
H2SO4 will be dissociated into what? 2H plus SO4 2 minus, right? Is it clear?
Yeah.
So will the standard conditions be maintained? 1 mole per decimeter cube of H plus ions? No. See, 2.
Oh,
Understood?
no.
Clear?
Yeah.
Got it? That understood? Enough? Understood?
Yeah.
1 mole per decimeter cube you have to maintain, right? 1 mole per decimeter cube you have to maintain that, right? Also, right? Arnav, list down the revision chapters you want to go through. Content, right? That'll be better, right? Mention bond number cycle or hydration enthalpy. Like this, can you do this? Make maximum uses, right? I'll be doing the revisions also with the current chapter, right?
Yeah.
Clear?
Got it.
Right? You make your own topic list. Let Harry make the own topic list. But yes, you both try to show me 5-10 questions, right? That will be really great. Fine.
Yeah.
Now, understood. We have to take a monoprotic acid such as HCl. Agreed? Fine.
Yeah.
We have to take a monoprotic acid, HCl. And what is the concentration you take? 1 mole per decimeter cube, right? Now, what happens in this reaction? In this reaction occurs, right? Two hydrogens, mainly this reaction occurs. H plus E gives you H2, right? So we can balance like this half, or we can use this also. 2H plus 2E gives you H2, right? Fine. Remember one thing. Now note down in your copy quickly. Harry, enough. The electrode potential will not depend on the number of electrons which is transact. Is it clear? Fine. See how many electrons are transact in this half equation? Enough? 1. Now
Yeah.
we can multiply this by 2. Harry, is it clear? We get this equation. But shall we multiply the electrode potential by 2? No. Electrode potential is not dependent on the electrons transact. Is it clear? Got it? Harry, is it clear?
Yeah.
Fine. Now, standard hydrogen electrode, right? Standard hydrogen electrode is arbitrarily given a electrode potential of 0. Clear? Is it clear? Fine.
Yeah.
Yeah.
Standard electrode potential of hydrogen electrode, standard hydrogen electrode is given a arbitrary assignment of 0, right? It is having 0 electrode potential. Clear everybody till over here? Fine.
Yeah.
Yeah.
Understood this part? Now we are moving on to the next part, right? Now before moving, right, I will take just a break and come back, right? Somehow can we find out the electrode potential of the individual half cells? Somehow that is impossible. But yes, standard hydrogen electrode will be helping us in this, right? Brilliantly. Means very, very diplomatically it helps us, right? How? See, what we do. Now tell me, what is the electrode potential of this half cell, Arnav? What did I tell you?
1.
Zero, right? Electrode
Sorry, 0,
potential is
yeah.
zero, right? It's zero, right? Now see, now what we do, we take individual half cells. Guys, please follow this, right? We're taking individual half cells and connecting in the cathode. Is it clear, everybody? Fine. We are taking different half cells. See, what are the different half cells? We are taking now what happens in cathode, Arnav? I have got a what colored cat in my house?
Yeah,
Red cat,
reduction.
red cat. Understood, Harry? Understood. Harry,
Yeah.
do you have a cat?
No, I don't.
Oh, I love cats, right? I die for cats. Thank you. So there's a red cat, right? Isn't it? Right, red cat. Do you know what? One of my students, they have gone from UK to, yeah, UK to Asia, right, for the job, right? They got transferred. They carried with the cat also with them, right? So that's amazing. One of my students 2 years back, they came from US to gone to Singapore. They carried that cat. Singapore
Mm.
to UK, they carried the cat. Two cats are there. And wonderful, lovely.
So,
Yeah.
that student who left, did they go to Singapore?
No, it was a
Okay.
student of they went to Hong Kong.
Oh, okay, never mind.
Yeah.
I was
Thank
thinking
you.
something else.
Is it clear? Fine. Did you guys sing? Now,
Yeah.
over here we have to see that whenever we are seeing that the copper, right? That the copper half cell we are taking, right? We are taking the two different half cells, right? What you're taking? We are taking this, suppose. These are the half cells we are taking, see, right? One by one, I'm placing this, right? I'm placing this half cell, I'm placing this half cell, I'm placing this half cell, placing this half cell, right? One by one. Is it clear? One by one. Over here in the cathode, right? In the cathode means what? We are forcing them to undergo reduction reactions, right? Reduction reactions. This is very important. Reduction reactions. We are forcing them to undergo reduction reactions, right? Now, what we do? We connect it with a standard hydrogen electrode. Now, whatever the voltage is coming, that voltage will be equal to what? E cell, E dot cell. Agreed? Agreed, everybody? Now, E dot cell will be equal to what? E right hand side minus E left hand side. This is the formula I taught you. Is it clear? Now, this this cell potential is coming how much, Arnav? 0.34. Now, what is the standard hydrogen electrode, Hari? What is the standard hydrogen electrode?
Zero.
Zero. Zero. Is it clear? This is X. Is it clear? Agreed? Agreed?
Mm-hmm.
So
Yeah.
what you are getting, 0.34 is equal to X. Is it clear? Understood? Is it clear to you? Fine. Is it clear? Did you get this thing? Right?
Yeah.
0.34 is equal to X. Means the voltage which is shown over here, that will be the reduction potential of this half cell. Agreed?
Yeah.
Fine. Brilliant way, right? Brilliant way we find out the electrode potential. See? Isn't it? Brilliant way. Is it clear?
Yes.
Do you get this thing? Now coming to this part, now we have to understand that whenever we are seeing that we are putting what? We are putting all the half cells. We are putting all the half cells one by one, right? We're putting all the half cells one by one, right? Isn't it? Over here, right? And we are noting down the cell potential over here, right? That is the electrode potential. Is it clear? Understood? Harry, is it clear? Arnav, is it clear? Fine. Is it clear? Arnav, did you get
Yeah.
it? Hmm?
Yeah.
What we're doing, we're putting all these individual half cells, right, in the cathode one by one, and you're noting down the values of the voltameter. Arnav, is it clear? Fine.
Yeah.
Isn't it? Voltameter, right? Isn't it? Fine. Did you get this thing? So this is very important that whatever values we are getting, we are noting down, and
Got it.
that will be the electrode potential of that half cell. Agreed, Hari? Agreed, Arnav? Fine.
Yeah.
We're noting down over here. Now write down this. See, this is a trick I want to teach you, right? This trick will be helping you a lot. Now write down delta G is equal to minus NFE. You learn this equation now, right? Fine. Clear? That will be easily helping you. This is the trick I want to pass on to you. Harry, note this down. Delta G is equal to
Yeah.
minus NFE. What is delta G, Arnav? Delta G is what? G is
Gibbs
what?
free energy.
Gibbs free energy. Brilliant answer. See, such a brilliant brain, both of you, right? Yes. This is what? Gibbs free energy, right? And Gibbs free energy should be, for a spontaneous reaction, it should be, Harry, it should be what? Negative or positive?
Negative.
Negative.
Negative, right? Negative. Enough prompt, see? Negative, quickly. Thank you so much. Harry also said negative, right? For a spontaneous reaction, Gibbs free energy should be negative, right? Isn't it? This is the thing, right? Should be negative, right? So that's the thing, right? So now, if Gibbs free energy should be negative, now Arnav, can you tell me that what should be the sign of E to make the reaction spontaneous? It should be positive or
Um,
negative? Think
it
and
should be
answer, right?
positive. Positive.
Yeah. Is it clear, Harry? Right? It should be positive, right? E should be positive. Is it clear? Arnav, is it clear? Harry, is it clear? So
Mm,
more positive, more spontaneous will be, more negative it will be. More is the spontaneity of that reaction. Agreed? Agreed? Harry,
Yeah.
enough
mm,
clear? Now, suppose you are taking two, you have taken two half cells to make a cell. Can you see that in some toys it actually requires 1.3 volts?
mm,
In some toys it requires 1.5 volts. In some toys it takes 1.9 volts. Right? So how do you make the half cells, right? How do you make the battery, right? We make it by this way. We have to combine, suppose we are combining zinc and nickel. Is it clear? Right? Clear?
mm,
We're combining zinc and nickel. Is it clear? Fine. Now Arnav, over here
mm.
we have taken these two half cells, right, to form the Voltaic cell. Arnav, is it clear? Harry, is it clear? Fine.
Yeah.
We combine these two cells to form the half cell, right? Now, which one to take at the cathode? Which one to take at the anode? That's a question mark, right? Now, we have to understand that in the cathode, which one to take? We have to take what happens in cathode? Reduction happens, right? So all our reduction reaction, can you see this? We have taken this in the cathode, right? In the standard hydrogen electrode, right? To find out the electrode potential, right? Now, which one to take the cathode? We have to
Mm.
take that in the cathode where the electrode potential is more positive. Is it clear? Which reaction is happening over here? Arnav, can you tell me? What reaction is this? Tell me. Reduction or
Um,
oxidation?
they're different. So,
No, though they're same. What reaction is there? Reduction reaction. See, all are reduction reaction. Can you see this? Plus
also,
E
I thought you
plus,
were blocking. Oh my god.
right? All are
Yeah.
reduction reaction, right? Is it? So if you see that when we talk about the reduction reaction, which reduction reaction will be more spontaneous, Arnav?
Um,
You have to follow
the
this, right?
first one.
First one you're saying, which is more positive, you told me the electrode potential should be more positive. That will be making us more negative, more spontaneous.
All right. Yeah. Mm.
So can you correct your answer? That which is more positive over here?
Third one. Yeah.
What
Third
about
one.
you, Harry?
That one, yeah.
Isn't it? So this you have to take as the cathode, isn't it? Clear, everybody? Clear? Understood how to judge from this? You use this equation, right? That is the trick I want to pass on to you. It will be making you absolutely clear. Is it clear? More positive, more positive electrode potential will be suffering reduction, and the other will be less spontaneous to reduction, right? So instead, it will be doing what? It will be contained in the anode. So oxidation you have to take place. Clear?
Mm.
Agreed? Agreed? Everybody is clear?
Yeah.
Harry, clear? Thank you.
Yeah.
Good focus.
Clear.
What about you, Harry? Where are you sitting? Long distance you're sitting. Where are you sitting?
I'm sitting next to my mic.
Thank you so much. Thank you.
Yeah.
Fine. Now see, now over here in your school in your board exams, you'll be giving that you have to find out the overall reaction and tell that which half cell you to take where and what is the cell potential. How to do such questions, right? We first write down the electrode potentials of the half cells from the data booklet, right? Arnav, Harry, can you Harry and both of you open the data booklet and tell me that where is the reduction potential given? Open it.
19, section
Send,
19.
send me a message, please. Electrode potentials given in section 19 data booklet. New data booklet, right? New data booklet. Fine. Done.
Yeah.
Arnav, have you opened the data booklet? You have to know that where is data booklet. I'm telling you one thing. Data booklet is a very important information sheet also, right? You don't know that your exams can be increased in the marks by using the data booklet correctly. From this year, you're lucky to get the data booklet in the paper 1. Do you know that? Earlier year paper one was not allowed data booklet, right? So data booklet has got lots of equations, lot of formulas, which you can use it, right? You flip the data booklet every day. What is there, right? Now, over here, Harry, which is more positive from these? Which you take as the
Uh,
cathode? Tell me.
the nickel one.
Nickel one. So this is more positive, right? We write it as it is. Is it clear? Right? As it is. Understood? Clear? We write it as it is, right? Clear? We write it as it is. Understood? Fine. We write it as it is. Now, next thing is that what we have to do this to this reaction? Tell me. We have to take it
Flip
at
it.
the anode. We have to flip it. Understood? Clear? Understood? Why flipping? Arnav, tell me what happens in the anode? Oxidation happens.
Decision.
To flip this, right? We have to flip this, right?
Yeah.
And oxidation, and you have to flip the sign also. Is it clear? Fine. Agreed? Fine. Now see.
Yeah.
Now, if you're giving a multiple choice question, that what is the cell potential of this half cells, then you can do this, right? E dot cell is equal to E right hand cell minus E left hand cell. Agreed? Fine. You can do this equation, right? E right is what? Right is the cathode. Left hand side is the anode. Is it clear? You can directly use these numbers, right? Isn't it? Cathode you have to put over here. Anode you have to put over here. Clear? Clear,
Yeah.
everybody? Now, if you're given the question that write down the overall cell equation and write down the cell potential, better to move like this. Is it clear? What we do? This is the cathode, right? We take it the cathode, and this we to take it the anode. Agreed, right? This take it the anode. Anode we have to flip it, Arnav. We have to flip this. We have to flip the sign also. See? Can you see this,
Yeah.
Arnav? Fine. After that, you have to add this to get the E cell, right? Clear? Understood? Also, you have to add to get the E cell. Is it clear? Agreed. We have to
Yeah.
add these two. We're getting now. Now, what's the overall cell reaction, guys? The overall cell reaction will be to add these two half cells, right? Clear? Fine. So two electrons gets cancelled. Make sure that the electrons are balanced, right, Harry? Enough. Fine. Make sure the electrons are balanced, right? Suppose you had got a half reaction, which is this, right? This. Suppose I'm telling you. Suppose what would have been done, Arnav? We have to multiply this equation by 2.
I do.
Understood?
Yeah.
And don't multiply the electrode potential. I told you earlier, I warned you that electrode potential is not dependent upon the electrons. Is it clear? If you're
Yeah.
multiplying this reaction by 2, you don't have to multiply 2 over here, right? Is it clear?
Good.
Fine. Fine. While take the board papers, right? I see that maximum silly mistakes are over here, right? They multiply by 2, right? Please avoid it. Hari, is it clear?
Yeah.
Understood this thing? Thank you so much. So now we are going to the part. Achha, did I send you my database question to you? Our database questions? Did I send you? Earlier,
Um,
2-3 weeks back, I didn't send. Or did I send?
I don't think so.
Okay, just 1 minute. I just cut pasted all the database questions. Just 1 minute. Yeah, here you go. This answer key is also there, right? It's going. Download this. Download this. Download. Please download. Thank you. Huh?
Yeah.
Please practice now, huh? From here. All the
Yeah.
past papers are there. Cut paste it. Right? It will be much more easier for you. Fine. Understood how to do it? Fine.
Yep.
Clear? So this is the thing. Now, if you don't flip it, right? What did I tell you? E right minus E left hand side, you have to apply this formula. Agreed? Fine. Now, going to this thing now over here, always remember that the E cell is this. Can you tell me one thing, Arnav, that why E cell should be always positive for a spontaneous cell to work? For a cell to work,
Because then it'll be double
delta
negative
G,
and gives fake.
delta G is equal to minus NFE. So this will be E cell now. Understood? For the electrode potential, what you take, Harry? NFE electrode. Understood? Electrode potential we put. Is it clear? Right, Harry? Is it clear?
Yeah.
Fine.
Yeah.
Thank you so much. Now we are going to the next part, right? See, this question. See, Arnav, please loudly read out this question.
9.5.
Yeah.
Work out the overall reaction and calculate the cell potential for a cell consisting of a Fe3 plus and a Fe2 plus half cell and a Zn2 plus and a Zn half cell.
Of cell, right? What we do? We go to page number 19, right? Section number 19, right? of the data booklet. We write down the electrode potentials from the data booklet. Understood? Clear?
Mhm.
Fine. And after that, we see what? Now, Harry, which one to take at the cathode? You use
Uh,
this formula, G is equal to minus NFE dot electrode potential. Arnav, is this clear? Harry, tell me,
Mhm.
which to take at the cathode? What is the answer?
so cathode is reduction.
No,
So the
not
first
cathode.
one.
Yeah, both are reduction reactions, right? See,
Oh yeah, yes.
both are reduction
Wait,
reactions. Where are you missing out, right, Harry? Tell me. We are all are reduction reactions. Can you go to page number, okay, section number 19, everybody? All are reduction reactions, sir, which is given. Can you see that?
yeah, yeah.
All are reduction reactions. We have to understand that which reduction reaction is more spontaneous. First, tell me. See, did
Uh,
you did you did you check Arnav? Did you have the data booklet, Arnav?
I don't have a daybook. No, I left in school actually.
So print out another copy. Keep one in school and keep one in your home, right?
Yeah.
Isn't it? You needed the data booklet, right? Uh, what? Do you have the soft copy of the data booklet, Arnav?
Soft copy. Yeah, I can pull it up. 1 second.
Yeah. Harry, just upload the soft copy in the Zoom chat. Thank you.
okay.
So I had a question.
Yeah, please tell me.
Why is delta G always negative?
Delta G is Gibbs energy. So
Yeah, why
Gibbs
is it always
energy,
negative?
because no, all not always negative. Delta G tells you the spontaneity of a reaction, right? Isn't it? Spontaneity of a reaction, right?
Mhm.
Delta S also takes the spontaneity, right? Isn't it? Right? We learned that Gibbs energy tells us the spontaneity of a reaction. The entropy also tells the spontaneity of a reaction, right? Now, if
Mhm.
the Gibbs energy is negative,
Mhm.
then the reaction is spontaneous. Is it clear? Please download the data booklet which you have sent, right? Thank you. Fine. Please download the data booklet. Thank you. So if the Gibbs energy is negative, then the reaction is spontaneous. Now is it clear? Understood? If the Gibbs energy is positive, the reaction is non-spontaneous. Clear? Now, entropy also tells you the spontaneity of a reaction. If the entropy is positive, the reaction is spontaneous. Clear? Arnav,
Mhm.
clear?
Yeah.
If the entropy is total entropy of the reaction is negative, that is non-spontaneous, right? Clear? But mainly we use Gibbs energy for spontaneity predictions. Clear? Arnav, is
Mhm.
it clear? Gibbs energy is what? Harry, just note down in the challenges part.
Yeah.
Write down enthalpy HL to be covered, right? Gibbs energy spontaneity mentioned there, right? Thank you so much, Arnav, right, for being
Yeah.
honest, right? Thank you so much. Please be honest, please, huh? Please ask me. Don't feel anything. You're best of buddies, right? Is it clear? Fine, Harry. Is it
Yeah.
clear to you? What's given? What's given in the that per 19? Tell me. All are reduction potential. Can you see, Harry? All are
Yeah.
reduction potentials, right? So which one will be taken at the cathode? Harry, tell me.
Wait,
Which one?
so I have a question about that table
Yeah, tell me. Just 1 minute. Let me open. Let me open. Let me open quickly.
because it keeps confusing me.
I'm coming. I'm coming. I'm coming. Just one. Give me a minute. 1 minute. 1 minute. Just here you go. Just 1 minute. Okay, over here. Uh, okay, you said 19, right?
Section 19. Yeah.
Yes, section 19. Yes. Go to the data booklet. You know what? Many people do not know that data booklets is a very important part, right? Now tell me. Harry, tell me.
Uh, so the more negative value, does that mean that species is better at
Oxidation. Oxidation.
oxidation,
Yeah, yeah, yeah. What are the reactions given over here, Harry? What reactions are given?
reduction?
Reductions. As Arnav brilliantly said, right? Delta G is equal to minus NFE. Agreed, right? Fine.
Yeah.
Delta G is equal to minus NFE. Agreed. So
Mm-hmm.
so what does it mean? This trick did I tell you that for the reduction reaction to be more spontaneous, right? E should be what? What should be the E dot electrode sign? Tell me.
Positive,
More
positive.
positive, right? More positive will be what? More negative. More negative means that the reaction will be zooming past, right? Very fast,
Mhm.
spontaneous reaction. Clear? Enough?
Yeah.
Yeah.
Understood this thing? Enough? So that's a very
Yep.
important thing, right? Clear? So
Yeah.
this is the way we have to find out, right? Suppose I'm taking this and this. Harry, tell me this, and suppose this. Which one you take at the cathode? Tell me.
The one that's more positive, which is aluminium.
Aluminium. What is your answer, Harry? Sorry, Arnav.
Yeah. More
Aluminium.
positive one.
Agreed. More positive, right? Isn't it? You have to check that what is the reaction given over here, right? Reduction reactions, right? Clear?
Yeah.
Fine. Now remember one thing, that if you see that when we see that a reaction like this, see, Fe3 plus to Fe2 plus, see, Fe3 plus to 2 plus, right? Just understand this thing. There are many people who make mistake of picking up Fe2 plus Fe. No, be very cautious of marking the signs over here. Is it clear? Marking the charge. Clear?
Yeah.
Understand? Clear? Now what we do, from the data booklet we pick up these two. Agreed? Agreed?
Yeah.
Yeah.
From the data booklet we pick up these two. Agreed? Now, Arnav, which one to take as the cathode now?
Sorry, what was the question? Which one do
Which one
you?
is to take as the cathode? We have taken two half cells. Which to take the
Yeah.
cathode? Both are which reactions, Arnav?
Red.
Reduction reactions.
Mm,
So one have to take at the cathode and other have to take at the anode.
the second one is cathode.
Second one you're saying, Arnav is saying second one. What about you, Schrodinger?
Second, because it's more
Second one,
positive.
yes, more positive. Clear?
Mm-hmm.
Yeah.
Right. Fine. Did Arfan bhai teach this trick? JJ NFE?
He did.
Fine. Okay. Is it clear? Fine.
Yeah.
So you're lucky. Do you know what the means? I'm really we take this at what? We take this at the cathode. Fine. And we take it at the anode. And anode, what happens? Hari? Oxidation happens or reduction happens? Tell me.
Oxidation.
So oxidation happens. This is a reduction reaction. Arnav, is it clear?
Mm-hmm.
So you have to flip it. And we flip this also. Is it clear? Fine. Agreed?
Yeah.
Fine. We flip this also, right? Fine. So see, we flipped it. Hari, Arnav, can you see this? We flipped it. Is it clear? Now,
Mm-hmm.
we have to find out the overall reaction, right? See, I was just very happy with Harry. I was going through his going through papers which is sent. He underlined, right? Fine. He underlined. Means I just wanted to show you. See, Arnav, this thing you have to do, right? See, I'm showing to you. Can you see this? Huh?
Mm-hmm.
Can you see this?
Yeah.
Always try to practice this, right? In your pressure, you won't have the same nerves which you're having now, right? Your nerves will be totally out overwhelmed. So underline. Can you see this? He has underlined, right? Fine. Always underline the question, right? But you missed
Yeah.
out underlining in many portions, right? Harry,
Yeah.
see,
I do so that.
sign. See, sorry, Harry, you didn't underline here. Why? You underline most, right? You underline most, see, but you didn't underline here, right? Here, see, underline many portion you underlined. I really appreciate you, right? I really appreciate you. Thank you so much. See, now what we're doing, we need to find out the overall cell reaction. So we add these. Now, electrons cannot be created or destroyed, right? They can be transferred from one reaction to other, right? In this reaction, one electron is there. In this reaction, two electrons is there. What you have to do, Arnav? You have to balance the electrons now. How do you balance it?
Um,
You have to
you just
multiply this reaction by 2. If you multiply this reaction by 2, Harry, will this be also have to multiplied, this electrode potential?
No.
No, right? We don't. Is it clear?
mm-hmm.
Easy? Understood this thing? Clear?
Yeah.
Fine. So this is the zinc we are getting. This is same to same we are taking, and we are adding now, right? Now, what did I tell you? If you are flipping reactions and adding it, you don't have to do right minus E left. You have to add these two reactions, right? To get the cell potential. Clear, everybody? Huh?
Yeah.
Understood?
Got it.
Fine. So
Mm-hmm.
that's the way we do now. Now see, now there's a very important part you have to understand. The polarity of the electrodes. Usually I see this is a very common question of the boards, right? Now write down this trick. Now, if you get a multiple choice question like this, right? Like this, what to do, right? Multiple choice question. Now remember one thing, you have to take the more reactive metal, right? More reactive metal means higher up in the electrode potential. Is it clear? Right?
Yeah.
At the anode. Now note down this, right? Clear? You have not given which is cathode anode, right? Isn't it? They're asking that which side the electrons will be flowing, right? Have you written this? So this will be anode. I get to know easily. Harry, is it clear? Arnav, is it clear?
Mm-hmm.
Fine. This is the cathode. Now, what happens in anode? Oxidation happens. So it will be losing 2 electrons, right? Losing 2 electrons, right? And these electrons will be coming from the external circuit. So in the question, the electrons carry the wire, the electrical wire carry the electricity through the external circuit, right? Clear? And the ions are carrying the ions are carrying the electricity through the solution. Clear? And wherever the electrons is released, that will be the negative electrode. Clear? Why anode is negative? Because electrons are released over here. Clear? Arnav, is it clear?
Yep.
Arnav, is it clear? Zinc gives you zinc 2 plus 2e. So electrons are released over here. Clear? Understood? Now,
Mm-hmm.
over here, what happens? Electrons is coming over here, right? Electrons coming over here. And what happens? Tell me. Nickel 2 plus is actually absorbing the electrons, see, from the solution, right? Clear? What happens? Electron is used up over here. So that's the reason this is positive. Clear, everybody? Understood this thing? Fine.
Yeah.
Mm-hmm.
If you're given a question, you can easily identify. Go to the section 19. See that who is higher up in the electrode potential. That will be the anode. Clear? Fine. Now, I'm just coming to this part. Next part in if I have to tell about tell. See, this will be coming in the boards. 100%, right? 100% coming in the board. Fine. The electrons will be flowing in the external circuit. From the where? From the anode to the cathode. Is it clear? Common question of a boards. 100% will be coming. Clear? Now, next is that we have to see that who is the oxidizing agent and reducing agent. How to do it? We do it in this way. See what we do. See how do you calculate the oxidizing agent and reducing agent, right? We have to see that now. Arnav, tell me, if you go from top to bottom, right? If you go to top to bottom, sorry, the we are going from the bottom to the top, Arnav, right? If you're going to the bottom to the top, right, Arnav, not can you tell me that what do you observe? That if you're going from the bottom to the top, Harry, the oxidation tendency increases, isn't it? Is it clear? Agreed? Agreed. Suppose I'm
Yeah.
comparing this to Arnav, see, Mg2
Mm-hmm.
plus and this and Pb2 plus, right here. So which one be suffering oxidation? Can you guide me? Which will be suffering the reduction? First tell me.
The more
Arnav?
positive one.
More positive. Which is more positive? Below. See. See, can you see
PB.
this? When you go from top to bottom, see? Negative, negative. This converts to positive. Can you see this? Understood? Clear?
Mm-hmm.
Fine. So if you go from the bottom to the top, what happens? The oxidation characteristics increases, right? The tendency to get oxidized increases, isn't it? Fine. So if
Mm-hmm.
you take this and this, so sodium will be more susceptible to get oxidized. Is it clear? More oxidized, right? Clear? And it does also. In the reactivity series, we see that as we move from the bottom to the top, what happens? The the reactivity increases. And what is the meaning of the word called the reactivity? The tendency to lose electrons. See, this is the reactivity series we learned earlier. Did see? Agreed. Carbon, zinc, iron, lead, hydrogen, copper, right? Isn't it? So see, more reactive metal will be what? Will be losing electrons, right? Will be losing electrons, right? Isn't it? If you have taken zinc and copper, zinc will be losing electrons and copper will be accepting the electron, right? Clear? So when we go from the bottom to the top, what happens? The oxidation power increases. Harry, is it clear?
Yeah.
Anu, is it clear? The
Mm-hmm.
oxidation power increases. So it will be behaving as a stronger. If somebody suffers oxidation, it is a Ra. Understood? Reducing agent. Understood? So it will be behaving as a more reducing agent, right? Clear? Now, if
Yep.
you go
Yeah.
from bottom top to bottom, anybody saying anything? Please stop. Huh?
No, no,
No?
continue.
Fine. If you're going from top to the bottom, what happens? Tell me. What happens? The reduction capacity increases, isn't it, Harry? Enough
Mm-hmm.
understood.
Yep.
Now let's check that if this theory is right or not. Nickel. You have taken nickel and you have taken iron. top to bottom, the reduction tendency increases. Does it, Harry? Sir, does it, Arnav? Tell me. Who
It
suffers
does.
reduction?
It does increase, yeah.
Who suffers reduction? Fe or yes, which?
Um, oh, nickel.
Wait. Which you have to take at the cathode? Reduction? All these are reduction reaction? Who suffers
Yeah.
reduction more? Tell me.
Fe.
Fe, understood? Fe plus 3, understood? So yes. So as you go from top to bottom, the positive number increases, right? Means what? The reduction capacity increases, right? So you'll be seeing what? This will be the strongest. So reduction means what? OA. This will be the strongest oxidizing agent. Clear, guys?
Yeah.
Understood? Fine.
Got it.
Thank you so much. So we are taking another break, right? We're taking another break and we're coming back
Yeah.
after the break, 2-3 minutes. You all just go to the kitchen, do this. It will be really helping you. So is it clear? It's fine. So we have to do what? Suppose we are getting a question like this: strongest oxidizing agent will be getting reduced. So to search for that, which will be having more spontaneous reduction reactions, right? So more positive value. So this is the more positive, right? So this reduction means oxidizing agent. For strongest reducing agent suffers oxidation, right? Fine. So what happens? You to search for the species which is more negative, right? More negative, right? So more negative what? More negative will be this one, right? Fine. So this will be suffering oxidation. So it will be the strongest reducing agent, right? Fine. So that's the way. Please try to make sure that you just update me the homeworks by today, right? Harry, send me a message, please.
Yeah.
5. Send me a message. Steve Owen Old. See,
Mm-hmm.
how many pages are there? 5, 6 pages. But you don't have to. I'm amazingly written. Go through it. Worked example. Go through it. 393.
Mm-hmm.
393 to page number um that's it. 406.
Yeah.
Clear? So that's a
Yeah.
portion you have to do, right? Now, Harry, can you just guide me that